This is the explanation or the solution to a problem we started in class. The problem was we have an 18 kilogram box. The box is released on a 37-degree incline, and then it accelerates down an incline at 0.27 meters per second squared. Find the coefficient of friction and the frictional force. So to set up the problem, we first draw a picture. So this is the picture representing the 37-degree incline and the box on the incline and the various forces. So I know that the box has a mass. They give me the mass of the box. There's also an acceleration, and this arrow going down the incline is representing the motion of the box down the incline. The frictional force, the lowercase f, is going up the incline because the frictional force is opposite the motion. Then I have the weight of the box. The weight is always going to be directed towards the center of the earth, so in this case straight down. And then I have the normal force. This is the force exerted by the surface that the incline is setting on, and the force will be normal, meaning 90 degrees to the object. I then establish my coordinate systems. So I set up my coordinate system so that my positive x direction is going down the incline, and positive y is going the same direction as the normal force. This then gives me an angle between the weight and the y-axis. So to set up the question is, what is the frictional force, little script f, and the coefficient of friction, which will be mu. The units will be the Newton for the particular frictional force, and mu is unitless. Concept I'm going to start with is the frictional force, and that relationship or that equation is the frictional force is equal to the coefficient of friction times the normal force. So what is known is the acceleration, theta, and the mass. What is unknown is the frictional force and mu. So again, we have to draw free body diagrams now that we're dealing with forces. The box is represented by the dot at the origin of this coordinate system. The frictional force is going in a negative x direction. The normal force is in a positive y direction. The weight, again, is at some angle, theta, with respect to the y-axis. So these are the three forces that are acting on the box. Now, since y is going off at this angle, I will have a x component and a y component for the I'll have a x component of w, and I also will have a y component of w. Okay. So now we need to set up the plan. The units are fine. Mass is in kilograms and accelerations in meters per second squared, so my unit should turn out okay. So now we're going to set up the plan, and we're going to start the plan with the relationship we started with, or the equation we started with was F is equal to mu F of n. Right, the frictional force is equal to the coefficient of friction times the normal force, but we don't know the normal force, we don't know the frictional force, and we don't know the coefficient of friction. So we can use the concept of Newton's second law in order to try to figure these out. Because Newton's second law says that the sum of the forces equals to the mass times acceleration. So Newton's second law again deals with unbalanced forces on an object. And if the forces are unbalanced, meaning I have a net force, after I sum all the forces, I get a net force, there will be an acceleration. So I'm going to do a summation in the x direction. So if I go back and look at the free body diagram and sum all the forces that lie along the x direction, what I get is W sub x, so the weight in the x direction, minus the frictional force, because again the frictional force is going in a negative x direction. This is going to be equal to mass times the acceleration. So let's solve for the frictional force. Negative frictional force will equal to ma, mass times acceleration, minus the weight in the x direction. What I don't know here, I know the mass and I know the acceleration. What I don't know is wx. I don't know what the weight is in the x direction. So we're going to use the concept of vector components. So w of x is going to be equal to w, the vector w, times sine theta. Sine, I'm using sine theta in this case to find x because the angle is measured from the y direction. If it was measured from the x direction, then I would use cosine. But since theta was defined in terms of the y-axis, they're now flipped. So sine theta will give me the x direction. So I now have w sub x, which I can plug into the equation above. So now I can solve for the frictional force. Once I have the frictional force, I can then plug that back into the original equation. So let's see if I now sum in the y direction, again looking at all the forces in the y direction. I have the normal force in a positive y direction. I have the weight in the y direction in a negative direction. And there is no acceleration in the y direction. The acceleration, remember, is along the x. You go back and refer to the picture. So it's going to be equal to 0. And in this case, what I'll do is solve for the normal force F of n. F of n is going to be equal to the weight in the y direction, which is unknown. But the weight in the y direction is going to be another vector component, so w cosine theta will equal w sub y. Once I have w sub y, I have f of n. F of n then can be plugged in back in. And I just realized something. Wait a minute. So once I have those, I have mu is equal to F, frictional force, divided by F of n. So then I can solve for mu naught. But in this, I made a mistake in that I don't know what W is. Okay, so I don't know what W is, but I know, again, using Newton's second law, W is going to be equal to mass times the acceleration due to gravity. So I can find W and plug that in. Okay, so now I have all of the variables now are solved. So I should now be able to plug in into my various equations and solve for mu and F.